Hello everyone, and welcome to my little talk about quantum satellites. My name is Veronica, and I'm the Outreach Officer of WISE, the Women in Science and Engineering Society. And today's talk is going to be a little collaboration between AstroSoc and WISE due to the World Space Week that happened in October. So I'm really excited to talk about this topic because it's quite new field emerging at the moment. A lot of work is still theoretical, or a lot of experiments are still being developed. So first, in order to understand what really are quantum satellites and why do we even need quantum satellites, why can't we just use normal satellites? Let's think about, well, what do we need satellites for? And in general, there are a lot of satellites orbiting the Earth, obviously, and they're functioning. They aren't, most of them aren't faulty devices. They're very advanced devices. They are able to communicate. They're able to store data. They're able to conduct research. So out of those 2,000 plus satellites, the majority is used for communication. And even if they're not used for communication, so maybe some of them are used for scientific purposes, they still need to communicate because they need to send data. So the key aim of satellites is to communicate with other devices and with the rest of the world. It started from the 1960s, where Echo 1A mission was launched as the first communication satellite, and ever since the number has just been growing. And unsurprisingly, especially in this age of big data and everything, a large amount of sensitive data flows through those satellites as well. And this makes a lot of satellite systems architectures very, very advanced and very complicated in terms of security, and a lot of details are often kept confidential. So everybody is trying to protect the data as good as they can. But a question could arise: are the security systems really secure, or are they impossible to break, or are they just very difficult to break? And this is a very important distinction. So the answer is yes and no, and we're going to see in a moment why. So it is quite impossible to prevent somebody from catching the signal from a satellite. If you have the right receiver, you can always catch an electromagnetic wave. So the way it is currently being dealt with is not to prevent people from catching those signals, but rather making them unable to decipher them. So there are various encryption strategies, and exactly as we have in the internet, data are being transmitted through different protocols. And there are two main types of encryption that are being used at the moment. So the first one is symmetric encryption, which does not distinguish between different parties and has no hierarchy. And asymmetric encryption, which involves usually a public key and a private key. And the public key is available to everybody, and then you need the private key to decipher the message. This kind of asymmetric encryption allows us to make hierarchy-based systems. So it's widely used, for instance, in the internet, on some client-server architectures, in SSL, and all kinds of communication. Well, one side requests data from another. And a lot of protocols require asymmetric encryption at the moment. So how about their security? Well, most encryption algorithms require 2 to the power of 128 or 256 operations to be broken, which for today's standards is still insanely safe. However, This is all on classical computers, so only allowing calculations on bits of zeros and ones. But there is another field emerging, which is quantum computing. And there is a lot of misconceptions about quantum computing. I'm going to describe what a quantum computer is a little bit later. But they function absolutely differently than normal computers. And it might be very easy to break something using quantum computers that would be very difficult to break using classical. And again, quantum computers are not for everything. So there are still some algorithms considered absolutely unbreakable by them. Well, absolutely meaning not possible to be broken in a reasonable amount of time. And most of them are symmetric algorithms. So those are still considered quite secure. There is a field called post-quantum cryptography, and people are researching different algorithms that are classical but unbreakable by quantum computers. However, the asymmetric encryption is considered highly vulnerable. It all started with Shor's algorithm, which proved that he basically proved that he's able to break RSA in a reasonable amount of time using a quantum computer if one was built. And the reason for that is, so RSA and ECC are two encryption methods. They're widely used up to these dates. People are slowly moving towards ECC, but honestly, here there is no difference in terms of being breakable by quantum computers. So it turns out that both RSA and ECC rely on some kind of unreversible, let's say, mathematical operation, which means it's very easy. It's quite easy to perform it, but it's very difficult to backtrack what was being, what calculations were being made. And in case of RSA, it is factorization to primes. Obviously, it's easier to multiply something than to factorize it. And in the case of ECC, so elliptic curve cryptography, it is the point multiplication of elliptic curves, so adding a point multiple times to itself, which can be reduced to. There is a mathematical method to reduce it to integer logarithm finding. So these are all algebraic concepts and considered, well, highly non-trivial when it comes to classical algebra. Well, classical computation, but using algebra, it was proven that both of those methods are reducible to period finding. Now, what is so remarkable about a problem being reducible to finding a period of a sequence? Because this is very easy to do using quantum Fourier transform. Quantum Fourier transform is a, let's call it a small algorithm, a subset, part of many quantum algorithms. And there is a recipe to do it. As long as you can use quantum Fourier transform, you can break anything that's reducible to period finding. So this should make us slightly uneasy, right? Because things that are protecting our data at the moment are quite easily breakable by quantum computers to a large extent. And the reason we're not being invaded by many parties at the same time right now, and the reason why it still isn't possible, is only the fact that we don't have as large quantum computers at the very moment. So we still have ones that use about maybe dozens of qubits, the larger ones, but the ones required here would have about 2,000 for the RSA, 4,000 for the RSA and 2,000 for the ECC. So still, 2,000, it's not such a large number, and people are predicting them to be built soon. So how how can we deal with that? What do we do about that? So perhaps if there is a possibility to break something using quantum computers, maybe there is a possibility to encrypt something using quantum computers. The answer is yes, it is possible. But before we delve into the details of how is that possible, first we need to understand what a quantum computer actually is. As I said, there are multiple misconceptions about them. The most common one is that they are normal computers but faster, which is absolutely not the case. It would be quite nice if it was, but honestly, quantum computers make a lot of difficult tasks easy and a lot of easy tasks difficult. The way computation is being made is entirely different. So, for instance, you can't copy any information on them. So they pose a significant challenge to modern researchers, but also enable us to do a lot of calculations that would normally take too much time. So when you have a normal computer, a single piece of data, let's say, so a single bit represents 0 or 1, is being represented by 0 or 1. In quantum computing, this is not the case. A qubit can be a 0, it can be a 1, and it can be somewhere in between. So it can have, for instance, 30% probability of being 1 and 70% probability of being 0. And you can't know what the qubit is unless you measure it, where the properties of quantum mechanics say that when we measure the qubit, it becomes either 0 or 1, so the function collapses. And this is already quite unusual to begin with, but what's even more important for quantum cryptography, what is being considered a 0 and what is being considered a 1 is also ambivalent. So here is the block sphere, and qubits can be represented by vectors or arrows on this sphere. And in this case, somebody chose 0 to be here on the z-axis, and then 1 to be also on the z-axis, but the opposite direction. And a lot of people are representing qubits that way, so 0 being up and 1 being down, for instance, because it's quite simple to deal with. But this is not the only equivalent of 0 and 1. For instance, if I wanted to define 0 as the green arrow here, and then make another arrow here to represent 1, I could do this, and I could perform measurements with respect to this kind of reference frame. In quantum computing, this is called changing the measurement basis. So it is possible to measure something in a different basis than just plain z-axis 0 and 1. So if I could send information that would be also consisting of only zeros and ones, for instance, but they would all be encoded in this axis or in any other axis on the sphere. So using this, there is a very clever thing that we can do with communicates when sending them via quantum channels. So this is the quantum encryption algorithm called BB84, which is maybe the simplest and probably also the most popular one. And people are implementing them in their experiment also most often. So here you have two measurement bases, and in the first one, let's call it the plus basis, 0 is defined as a vertical arrow and 1 is defined as a horizontal arrow. But the x-axis is the x-basis is the same, but the axes are shifted by 45 degrees. Now, what these arrows correspond to, they are usually pairs of polarized photons. So if you take if you look at the polarization of the light, you can deduce the, let's say, direction of the arrow, and then read the information from the photon itself. So this is how the data is being sent. And in this experiment, in this protocol, Alice, who is sending out the bits, is using two different bases to send zeros and ones. So she chooses absolutely randomly which ones is she going to use at the moment. So for instance, here she chooses 1 in the diagonal axis. Here is 1, but in the perpendicular axis. Here is 0 in the diagonal one, etc., etc. And the key thing to note here is that if you measure something sent in one basis in another basis, you would get nonsense. Well, you would get 50% probability of either of those. Why? Because those arrows are exactly in the middle. So, for instance, if I expect if I want to check if it's up or horizontal, so vertical or horizontal, and it turns out being 45 degrees, then quantum mechanically, there is exactly 50% of probability of it being either here or here, because it's exactly in between. So long story short, if you measured something in the wrong basis, you would get absolutely random numbers, so 50-50. So Alice sends those photons that corresponds to single bits, and what Bob does is he chooses the basis and he randomly measures it. So some of them are going to turn out the real information, and some of them are going to turn out random noise. Now, important thing, how does Bob know which ones are the ones measured properly and which aren't? And this is solved by Alice sending out classically not the information that she sent, but the information about the measurement basis that she chose. So, for instance, she sends this kind of string of bases and says, okay, for the first 2 times I use the plus axis, then I use the x-axis, and then I use the plus basis once again. And then if Bob knew which bases were used to sending out this data, then he can compare it with the basis that he used and compare the validity of the data he got. Some of them are going to turn out wrong, obviously, and then, well, in most cases, and then Bob can absolutely just cross them out, not care about them anymore, and only care about those bits that were specified as being measured in the same basis as Alice sent them. And what they achieve in that way is they have a string of bits that they are both sure they have the same result, so they were received and sent properly, and they can serve as the encryption key for further communication. Now, how is that different from normal setup? Because there is still some information being sent classically, and the answer is yes, there is, but the information being sent classically corresponds to the measurement basis and not the actual information. So if somebody eavesdropped on sending classical data about the measurements, so if somebody eavesdropped on a communique that just listed out the basis that somebody used, it would not be useful for them at all. And the only thing you could do to eavesdrop on the system would be to intercept the photon themselves. But due to entanglement properties, you can also entangle those photons with other ones, and this will make eavesdropping detectable, because if one of them is being interrupted, then the other one would be as well. So eavesdropping on quantum systems is, as you can probably imagine, not a good idea. It will be easily detectable. And so using this protocol, quite secure communication can be established. Now, the next question would be, is this possible? Is this just a thought experiment, or are people actually implementing this? And the answer is they're starting to. So, for instance, there is one quantum space satellite which was launched in 2016 by the Chinese Academy of Sciences, and they are actually implementing these kinds of protocols using real-life hardware. The first attempt they did was a quantum encrypted video call in 2017. Realistically speaking, it was not secure because the satellite stored both keys between two parties. And in this case, if we don't trust the satellite, then we still cannot use a satellite that knows everything about both parties that are communicating via these satellites. So this was kind of a half measure before implementing quantum secure cryptography of two parties on Earth. So there was a second approach, actually in June 2020, where they distributed one photon from the entangled pair directly to its station. And the distance between those entangled photons was approximately 1,120 kilometers. So you can imagine establishing quantum coherence on these kinds of differences of distances would be very difficult, if not impossible, using optical fibers or any on-Earth channel of communication. And in this setup, satellite itself was unable to decrypt any communique. So you could be using the satellite of your enemy, or you could be using any kind of satellite that would be owned by anybody on the Earth. Nobody would intercept the data. And even if they did, it would be random nonsense. So this is probably the most known quantum experiment, but this is not the only one. And there are also other experiments, but unfortunately a lot of the work is still confidential. As you can probably imagine, especially given the topic, a lot of experiments are being kept under the key and not shared with the public before they are fully functional. However, there are some publicly known endeavors like the CubeSat, called gracefully Spooky One, from the National University of Singapore and University of Strathclyde, so a joint venture between Singapore and UK, which can send quantum correlated photons. They haven't fully established quantum entanglement yet. It's just correlation, but the advantage of this satellite is that it's it's a CubeSat, so it's very small and it's quite easy to produce, and they're making a step towards industrial level kind of quantum encryption communication satellites, so that they aren't as big and as difficult to produce as the Chinese one. There is also one being built by the USA, by DARPA, but there isn't really much information on that. And there is also something called a KeySat, led by the Institute of Quantum Computing at the University of Waterloo, which is another attempt to build a quantum correlated, quantum entangled, quantum encrypted satellite as well. So this brings us to the end of the talk. The topic, as I said, is an emergent field. So the sources that I've used are literally from 2020. And I recommend you read the paper if you are interested in that. So the first one is based on the Chinese satellite, and the second one is built on the joint UK one. It is a pretty exciting field to be reading about, so I really recommend. And further reading for those interested in quantum computation, which is, as I said, at the very basis of whatever that's being developed by the quantum satellite developers. I recommend the book Quantum Computation and Information, especially chapter 12 for quantum cryptography, which tells you a bit more about what actually are quantum error correction algorithms, how to know we are not just receiving random noise, how to detect eavesdroppers, really, really interesting stuff. And yeah, I think I would like to wish everybody happy Space Week, which already happened, but AstroSoc has prolonged it to last more than it normally would. So a big thanks for that. Big thanks for hosting me. And check out more events of AstroSoc and WISE if you have the time. So that would be it, I think. Thank you very much once again for all your attention, and hopefully see you sometime next time.